Good morning. Yes, it's still morning. Happy Thursday. You guys, we only have 4 weeks left of regular class. That's crazy. But we're going to talk about all the stuff for the review. So here we go. Things to think about. Thing one is just kind of the basics of various types of alternative energy. So I think I list them. I don't list them on the review. Just the different things. We talked very specifically about windmills. We talked very specifically about pumped water hydro storage or hydropower. And we talked specifically about solar power. And then we talked about different types of fuel and the energy density of that. So being able to take, we need to get this much, this percentage of efficiency, and then getting from there how much, based on whatever fuel you have, how much you would need. And so be mindful of just the different types, both conceptually how they work, how the energy transfers through each of them, and then mathematically how to calculate the different situations. So energy production is one of the concepts that we're looking at. Along with that, like I said, energy density. I'm just looking at the concepts on the topic review and talking about those right now. So energy density is another one. So how many megajoules per kilogram can you get, and then why that becomes important. Black body radiation, we did a bunch with. And so again, let me grab something to make sure I get it written as just kidding. So we talk about black body radiation. The amount of power that's going to be emitted is the emissivity sigma a t to the fourth. And so when we're looking at the power from a specific black body, we have this equation for it. E is your emissivity. And if it's a perfect emitter, then it's an emissivity of 1. So if you're dealing with a star, your emissivity is 1. You don't even have to put it into the equation. If it's a planet that's gaining energy and then re-emitting it, you probably have an emissivity, might be 70, 80%, something like that. Sigma, 5.67 times 10 to the negative 8. It's our constant there. Boltzmann's constant. Area is the surface area of the star. And so you'll use 4 pi r squared. And then T is the temperature, and that's measured in Kelvin. So you're taking these different things and putting them together. If you want to get the intensity, remember intensity equals power over area. So if you take and divide this by area, you would just have E sigma T to the fourth. Like that. So that's another thing that can be used based on the temperature of a star. So black body radiation, be familiar with how to calculate the power from a given source, and then be familiar with being able to calculate what the intensity is at a different spot somewhere out in space. The other thing that we talk about, so there's 2 terms that we deal with that are somewhat similar, easily confused, but they're not the same. So albedo is going to be what we talk about, we have albedo and we have emissivity. So emissivity is what we're talking about here. It's the percentage of radiation from that given body compared to the percentage of the radiation for a perfect black body. And so it's saying, like, if I have an emissivity of 70%, 70% of what it could be is actually what's given off. When we talk about albedo, albedo deals with reflection. And so albedo is the amount of radiation that comes in that's reflected by the body that's receiving it. And so if I have an albedo of, 15%, that would mean that 15% is reflected. And then that would mean that 85% could be absorbed, or reaches the surface, we'll say that. And so when we're thinking about the way that the solar power works, and if we have the albedo of something, because the atmosphere or whatever surface you're dealing with, whatever you have, the rest of it would actually be able to reach the surface. And so just be mindful of those two ideas. We talked about Sankey diagrams. Sankey diagrams are visual representations of where energy is going within a given system. And so when we talk about a whole a power production thing, then we can use that. Yeah?
So with that albedo thing, that's like the end result, but it's not like actually output, right? Like it gets absorbed and then reflected, right?
No. You're talking about, I think you're talking about like with power where it would be absorbed and then re-emitted. Is that what you're talking about? Like.
Oh, is that what emissivity is?
Yes.
Okay.
Yes.
Oh, so that's the difference between albedo and.
Yep. Albedo is just like this is reflected and never gets there in the first place.
Okay.
And this is emissivity, is it's absorbed. So the Earth behaves as a black body, but it's not a perfect black body. And so it absorbs the radiation that's coming in. And this happens day to night. So it absorbs it during the day. In the nighttime, it releases it, but it's not 100% what was absorbed.
Okay.
That happens with us because we have the atmosphere, and anytime for energy to be released, that transfer of energy in the form of heat, you would have to have a lower temperature on the outside than what's on the Earth. And so it can absorb, but it's not gonna re-emit, as like it can re-emit only to the point that it reaches the air temperature. So you're not gonna have the ability to really get everything back out.
Alright.
But yeah, that's the difference with those.
Okay. Yeah.
Sankey diagrams are just the arrows. You've done some stuff with that. I think there's a practice on here. And then the lesson I have, energy production calculations. So that means for windmills being able to use that. That means for pumped water hydro storage, or hydropower. Why do I keep saying that? Pumped storage, hydropower. That you have that. It means being able to calculate using energy density, and it means being able to calculate using nuclear energy, and there's some practice in here too. And then, let's see, so it says describe the major energy transformations, so things like where do you have electrical energy, mechanical energy, heat transfer, energy loss, stuff like that. Power produced in different situations, solar power, fossil fuel, I forgot about those two. Black body radiation, all that stuff. So in your review, you've got several different problems where you're working through different situations. One of them looks with a windmill. And so this one is when we're dealing with black body radiation. This equation is for windmills, where we have the power equals 1/2. A V, I remember this, okay, P, nope, let me get this right. Rho V to the third. I forgot the equation off the top of my head for a minute. So what we have here, area, this is that cross-sectional area of the disk that is created by the rotating blades. And so you use pi r squared. So you're usually going to use the length of a blade here. Rho is the air density. If it's air, it's usually around 1.2 kilograms per meter cubed. It can shift, but that's generally about what it is. V is the wind speed. And then power is in watts, obviously. Usually when we're talking about, not always, but usually when we're doing a calculation with this, we're dealing with the idea that there will be some power loss along the way. So be familiar with the equations you may need for that. Number 2 deals with a fission reaction. And so it gives you the fission reaction, and you're using it, it just gives it to you. You won't actually have to do anything specific with calculating the reaction, it just gives it to you in there. And it says, estimate the initial mass of U-235 needed to operate a 600 megawatt reactor for 1 year, assuming 40% efficiency and 200 mega electron volts released per each fission reaction. And so the biggest thing where people get tangled up is remembering the mass of U-235. And so because it's a really specific piece, atom that we're doing with that, we can say it's 200, we can just use 235 grams of U-235 is 1 mole of it. So we can do that, you can use that as an estimate there because it's specifically that atom. And so if 235 grams is gonna equal 1 mole of it, then we can kind of carry on with that to make those calculations. So that's a lot of going back and forth between what we know about a gram to mole calculation, what we know about the way that we can get that energy from the amount of energy we have, and then the idea of joules and watts and how those go back and forth. So that's what you're working on that one. You have a black body question that you'll need to work through. So here's our black body equation. Remember that the power that's emitted from the source is always the same. So if it's, emitting, 12 times 10 to the 12th watts, that's the same amount that's emitted. The intensity will change the farther out you get. So when you're calculating the intensity out here, you're calculating how it spreads out to this whole kind of area around there. Pump storage hydropower, we just finished up. And so you're looking at a relationship between potential energy and the electric energy that you can get. And then number 5 looks at a fossil fuel power station. And you're dealing with the energy density and then what you can get from there. One of the biggest things, I'm going to erase this real quick. One of the biggest things to think about in any of this is just the reminder that when we're talking about power and energy, power is your energy per second. And so sometimes you might look at a question, it might be something that is using some bit of something that you maybe haven't experienced before. I need to add, I'm going to add one more thing on here. I don't have a solar power question, so I'll add one of those to what we're doing. But what you end up having is watts and joules per second. So in any of these, watts is joules per second. And so a lot of times one of the pieces that we're relying on with this is this conversion. The other way to think about it is power is equal to energy over time. And so if you know that you have a certain amount of energy and you're using that for 8 hours, that can be your start for getting it into the amount of power that you have. The time does have to be in seconds. So we have joules per second there. So we have that, and then another piece of the question is asking about the graph that we have for black body equations, where we have something that looks like this. We look at our peak height of to help figure out our temperature for what we have. And so here we have intensity. And again, that's sort of an arbitrary relationship. Here we have our temperature in Kelvin. And so we're looking at and then with that temperature, it'll help us figure out what our peak wavelength that's being emitted is going to be. And so there'll be some questions on that as well. Lastly, it's not on there yet, but I'll add it on when we're done here, is thinking about solar power. Take this stuff down. Talk about solar power. Maybe. Solar power, obviously we have light coming in from the sun, and that's going to come in at a certain intensity. Coming in, the solar constant coming into the Earth is 1,400 watts per meter squared. at the distance of where we are from the sun. And I think this number is actually given in on your constants page in your data book. Not all of that reaches the surface. We do have, ends up being about, I think about a 50% albedo based on just kind of overall Earth composition. So you have this, it would get there, but then you have your solar panels that would be collecting that. And so there's two pieces that happen with this. One, if it's a solar heating panel, you would have a mass of water in there and can figure out how much is heated. Two, if it's a photovoltaic cell, you would figure out how much electricity is being used, along with whatever, you know, percentages of albedo, efficiency, all those pieces, and calculate the power output into that home. So different things to think about with that. All together, when we're dealing with alternative energy, the thing that we're looking at is how different sources of energy can be used to create something that's electric. And so, or heating, or whatever that situation might be. So we're kind of depending on different pieces that we've been looking at before. So we're depending on ideas of electricity, or depending on ideas of just mechanical energy, depending on heat, that sort of thing. So that's where we're headed with that. On next Tuesday, we're gonna have Textbook Tuesday again. And we'll be, I know, right? We'll be working on this stuff in class. So just know that you will have some time, and then I'll post the test for Wednesday.